Can you see my screen?
You can start now.
Okay. So hi everyone, we are live at YouTube now. We hope everyone is safe at these troubled times. So we are glad to receive here in the second ICTP-SAIFR IFT-UNESP physics discussion, the professor and director of the Max Planck Institute of Optics, Ignacio Cirac. So Ignacio Cirac is a Spanish physicist who did his PhD at the Universidad Complutense de Madrid in 1991. Then he moved to do his postdoc at the University of Colorado Boulder, where in collaboration with Professor Peter Zoller, he became one of the pioneers of quantum computing and quantum information. Since then, he has made major contributions in quantum information theory, quantum optics, and many-body physics. In 2001, he became the director of Max Planck Institute of Optics and has been granted multiple awards along the years, like 2006 Prince of Asturias Awards, 2013 Wolf Prize in Physics, and 2018 Max Planck Medal. So with the word, Ignacio Cirac.
Okay, well, thank you very much for the invitation. It's my great pleasure to be here. And I want to give a talk about quantum algorithms. So this is related to quantum computing. And the first thing that I want to say is who are the collaborators with whom I did some of the work that I'm going to present. That's Jimin Ge, who did a PhD in our group here, and Jordi Tura, who was a postdoc and now he's a faculty in Leiden. Siru Lu, who is a master student in our group, and Marie-Karen Banyuls, who is he's a permanent staff member of our group. Okay, so there are problems that appear, especially in science, in physics and in chemistry, that are very hard to solve. And by hard to solve, I mean that if you want to make predictions about the behaviors of these systems with a computer, with a classical computer, then you can only deal with very small systems. And that if you try to solve bigger and bigger systems, like bigger molecules, bigger materials, or some high energy physics, like let's say in a big volumes, then this typically runs into a problem that the classical computer, the computer cannot solve those problems. And the reason can be understood very easily. Just first of all, because in all these problems, either we discretize space, like in high energy physics, then we will make a lattice to describe physical space, or the space is discretized in some particular way. So for example, in condensed matter physics, you have a periodic material, then you have an atom at each of the sides. Or in chemistry, because you have certain orbitals, and then you can express the problem in terms of these orbitals. So at the end, what you have is that what you want to solve with your computer to make predictions in these systems is a lattice in which you have particles in the lattice that interact with each other. And that's what we call a many-body problem. So in physics and in chemistry, then you describe these interactions in terms of something that we call a Hamiltonian. And we would like to make predictions. So what will be the behavior of your molecules or your material or some your high energy particles. And for that, then you have to solve a problem. And see that this problem gets harder and harder and harder while you increase the size of your system. Whenever you increase the volume of your system, can be seen already. You take just the simplest case in which at each of your lattice, you would have the simplest quantum system, namely a spin 1/2 particle or a qubit that can have two states, the state 0 or the state 1. If at the end, I want to make a prediction about the physical properties of my system, and I look at that description of the system, then according to quantum physics, I will have to express the properties in terms of a quantum states. And this quantum state can be in a linear superposition of all possible configurations of that system. So you had, for example, spin 1/2 particles, then you could have that all the spins are down or the last spin is up, and then there are 2 to the n configurations, and the quantum state is a linear superposition, and the physical properties are encoded in the complex coefficients of these linear superpositions. And you see that the number of coefficients grows exponentially with the number of lattice size that you have with the number of qubits. So if you want to store these coefficients in a memory, in a classical computer, then this memory will have to grow exponentially with the number of qubits. Apart from that, you want to make a prediction again, you will have to compute what are these coefficients. And for each of the coefficients, you will have to do at least one computation. And so the number of computations will be at least the number of coefficients. And since the number of coefficients grows exponentially with the number of qubits, then it will require a time that also grows exponentially with the number of qubits. So both memory and time grow exponentially with the number of qubits that you have. So as soon as you have something like 15 or 20 qubits, then this problem becomes impossible, because you cannot neither store the state in your computer, nor you can wait until you finish your computation. In fact, one could, and this will be important for what I said later on, one could try to trade memory by time. So for example, imagine that you have a computer in which there is a limitation in the memory that you have, or for example, the memory can only grow linearly with the size of your system. You can imagine that we have 10 to the 20, let's say, baryons in the universe, so you cannot probably not store more than, this number of coefficients, and therefore this was a limitation. So still, we could use this computer with a memory that is smaller, and then we have to trade it for time. So this means that we will have now some, going on. So then you trade memory by time. So you have a memory that now it's constant, let's say. Then it turns out that the time that would require to find a solution with a classical computer will be super exponential, even in n. So it will scale like 2 to the n to the power n, so 2 to the n squared. So it is much faster, much worse even than exponential. Okay, so that's now quantum information theory. It allows you to address these problems and circumvent this exponential explosion. And then there are different ways of doing that. There are different offers that quantum information can make. So one of them, and this is something that we do in our group a lot, is to use tensor networks. And the idea here is to realize that actually when you have a physical problem, the states that you are going to have are not arbitrary states, because they are related to the interactions, and the interactions are very peculiar in nature. So they are already few-body interactions, so two-body interactions or three-body interactions, and you have locality in one way or another. So the fact that you have these kind of interactions in nature means that your states actually these coefficients will not be completely general. So in other words, in your Hilbert space where your state is a member of, is part of, then all the states are irrelevant for physics, and only the ones that are in some corner of Hilbert space are relevant. So one could ask the question, so maybe by trying to write the state in this basis, in terms of the configurations, we are treating all the states in Hilbert space on equal footing, and this is why we have all this exponential overhead to pay. And one could say, so what happens? Can we have a description that maybe is very bad for all the states in Hilbert space, but for this corner of Hilbert space, this where physics is important, is very efficient? And actually, this is the goal of tensor networks, to describe not in this basis, but with a different language, this corner of Hilbert space, and therefore to avoid or circumvent these exponential explosions that I mentioned. So there is another possibility, and that's what leads to the field of quantum simulation, is to say, well, if I want to solve a problem that is a quantum many-body problem, why don't I use a quantum system, not a classical computer, but something like a quantum computer? And then you see that you gain right away, because you want to store, so you have a physical system now that is quantum, where you have quantum bits, these qubits, and you want to solve a problem now corresponding to condensed matter physics or high energy physics or something else. Then what you can do, instead of writing these coefficients, then you can prepare your quantum computer in that state. So in other words, you want to represent n qubits, then you just need n qubits in your quantum computer, and do the computations with your quantum computer in this quantum system, and then you will save a lot. And actually, that's the idea that Richard Feynman pioneered many years ago, in which he realized that if you use a quantum system or a quantum computer to solve many-body problems, then right away, the memory that you need only grows linearly with the volume of your system. Okay? So the number of qubits that you need is equal or proportional, if you want, to the number of qubits that you want to solve, the problem that you want to solve. And the time, then at that time, he didn't care so much, but it may happen that there is also some gain in time. And this gives rise to the possibility of solving problems in many-body problems with quantum computers that you cannot solve with classical computers, so that you overcome these exponential overheads that you had in the case of classical computers. In fact, so the field of quantum simulation, now it's pursued in many labs, and there are two incarnations of how to solve problems with quantum systems, quantum many-body problems, just by using quantum computers or quantum systems. So one of them is what is called a digital approach, in which what you would do is to use a quantum computer, with gates, quantum gates, and so on, to solve this quantum many-body problem. The other approach is called the analog, and this is like an analog computer in which you take your quantum system that could be, for example, a different platform. Maybe you want to solve a problem in high-energy physics, and then you take cold atoms. And these atoms, then you engineer the interactions of these atoms, which are now stored in some lattice, and you make it in such a way that they interact according to the Hamiltonian that you want to solve. So this you are emulating with your system the problem that you want to solve, and then you can just perform measurements on that systems, and this will tell you about the predictions that you want to make in your problem. In fact, now at the moment we have analog quantum simulators, so there are different systems that are being built to solve problems in an analog way, and we have some quantum computers. However, these quantum computers are special ones, because they have errors and they're very small. They are prototypes. They are called noise intermediate state quantum computers. That's like the one that Google used for the supremacy experiment. And so the question is now how to solve many-body problems now, maybe with these two kinds of computers in the short run, because they already exist, or with these in the long run. And that's what I want to talk about. So certain algorithms that allows you to solve problems, many-body problems, faster than with a classical computer, either using, let's say, a full-fledged quantum computer in the future when it will be built, or with one of the existing quantum analog or NICs devices. So what kind of problems I'm interested in? So let me be a little bit more precise. So these are problems, the lattice problems, in which somebody has given us our Hamiltonian, and the Hamiltonian can be written as a sum of some Hamiltonians. Hn is a small hn, and I will assume that these Hamiltonians are local. In fact, you can lift this condition that the Hamiltonians are local, and it's still most of the things that I'm going to say will work as long as these are few body interactions. But anyway, let's concentrate in local. So local means that if you have your lattices and you have some particles, some quantum particles in your lattice, maybe these are qubits, or maybe some are qubits and some are, let's say, fermions, and you have this problem, then that the Hamiltonian only acts on some neighborhood. Each of these terms acts on some neighborhood, and at the end you have a sum of that. That's what we call a local problem. So we will consider here lattice with qubits or spins and fermions. I will not touch it here, but it's possible to adapt it to fermions as well in any physical dimensions. So typically I will draw two-dimensional systems, but it also works in three spatial dimensions. And we will assume that we have local Hamiltonians. So that's the problem that is given. And what we want to do is to talk about the dynamics in the system. So what happens if I just go out of equilibrium and I let the system evolve? Can I make predictions about what will be the physical properties of the system? So for example, if I have a set of spins interacting with each other and I flip some of the spins, then they will start evolve, and at the end they will have some magnetization in some particular place, and I can look at this place. Or you have lattice gauge theories, then you can have some gauge fields, and you can have some fermionic degrees of freedom, and then all of a sudden then you maybe create some put some charges somewhere, and then there will be some string breaking, and some things will happen, and you want to describe that. So you want to describe the dynamics. Another kind of problems that I will look at will be thermal equilibrium. So what happens now if there is no dynamics? You're in thermal equilibrium, so your state is described by a Gibbs state. And I'll consider zero temperatures. I will consider also finite energies, and I'll explain what I mean by that, and also finite temperatures. And of course, we will not be interested in knowing what is the whole wave function that describes the whole system, but we're interested in expectation value of observables. So that's what I told you before. I want to know how the magnetization in some particular region behaves, how the correlations build. If you have lattice gauge theory, you will want to compute some Wilson loop and to compute the expectation value and see if it grows with the area, with the volume, in order to know if you have confinement or not. So these questions which are related to that. Okay, so that's then I can introduce now what is the goal of this talk, is to talk about quantum algorithms to solve many of the problems, in particular about dynamics, zero temperature, finite energy, and finite temperature. I will talk a little bit about dynamics and zero temperature, but I will go relatively fast, and I will spend more time talking about finite energy and finite temperature. And I want to make a connection to these algorithms and current devices. So I will also mention whether these algorithms would run in, let's say, to be built quantum computers or on analog computers or on NISQ devices. And also I will pay attention to whether you can gain any advantage with respect to classical computers. Of course, I mentioned that right away we gain in memory because it's only polynomial. So I will see how long does it take to solve these problems, as a function of the number of the volume of my system, the number of qubits that I have, and this could be linear or exponential or doubly exponential or something, and I will have to compare with the best classical algorithms to see if it makes sense to use a quantum computer for that or a quantum simulator. Okay, so now let me start with the dynamics. Okay, so what is the problem that I want to solve? So again, I have this lattice, and I have a Hamiltonian. That's what we are given. And let's imagine that somebody tells me what is some initial state, psi 0. And I assume that this state is some state that can easily prepare. So for example, is a product state. So if these are spins, then maybe it's all spins down, state 0 or something like that. And once I have that, and somebody gives me a Hamiltonian, I would like to know what is the dynamic. So I will evolve according to the Schrodinger equation. So that's the state after some time t, evolve with this Hamiltonian h. And once I have that, then I would like to compute the value of some observable, some expectation value. That's the goal. And so the quantum algorithm, to do that, what they do is to say, okay, so what we do is with my quantum computer, now we take a quantum computer that is based on qubits, and then we prepare in the quantum computer this state psi. I will tell you how to prepare it, and this is the quantum algorithm, tells you how to prepare it. And once you have prepared it, then the only thing that you have to do is to measure this observable. Or you will measure, you repeat the experiment, measure again, repeat the experiment, measure again. At the end, you take the average. And so this will predict this expectation value. And of course, if you want to have it with certain precision, then you'll have to repeat the experiment many times. We know very well how the precision, how the error decreases with the number of measurements. It decreases like 1 divided by the square root of the number of measurements. So with that, you know, if you want to get the value of your observable up to some precision, then you will have to repeat this algorithm a number of times. No, that will be 1 divided by this precision square, basically 1 epsilon square. And now the key point is, so how does it scale to prepare this state? So the quantum algorithms that have been proposed is given some initial state, how to prepare a state. And the first algorithm, which is very successful, was proposed by Seth Lloyd in 1996. And he basically translated the idea of Richard Feynman that posed it in that paper and did some simple calculations with that in order to show that the quantum computer can solve this problem very efficiently. And his idea is the following. So first, let's assume, for simplicity, that the Hamiltonians that appear here commute with each other. And if they commute with each other, then you see that if I take the exponential of a sum of operators that commute, I can write it as a product of exponentials. And you see that each of these exponential corresponds to the evolution of something that acts locally. So you can translate this in terms of quantum gates. So what this means at the end is that in order to apply these operators from initial state, you prepare the state, then you will apply few quantum gates, then another set of quantum gates, another set of quantum gates, another set of quantum gates, and with that you have prepared the state, and then you will come when you will do the measurement, as I mentioned before. So for general Hamiltonians, then you cannot do that. This is not true. If your Hn don't commute, then you cannot write that this is a product. However, there is a trick for doing that, and this is what he proposed, Seth Lloyd proposed in that paper, is to use what is called Trotter expansions. The basic idea is that you say, okay, so I can write e to the minus IHT as e to the minus IHT divided by m, and then to the power m. And so you look at this operator here, then you realize that this is the same that what you had before, but now this t is divided by m. So you can, if m is very large, this t is very small. And so now the idea is that if t is small, then you can approximate this operator here by the product of operators. And the reason is because now the commutation relation between these terms, when you try to use Campbell-Hausdorff formula or anything to do this expansion, then the commutation relation will be proportional to t squared divided by m squared. This is what is going here. And so you see that if m is sufficiently large, you can make this error very small. So this is a very good approximation. And then you will have to, this is just the gates that I told you before, so you will have to do these gates more times, but still the number of times will not be very, very big. And this is what Seth Lloyd computed. And he showed that if you have local Hamiltonians, like the ones that I was considering here, then the total time required for a quantum computer to solve this problem would scale quadratically with the number of qubits, quadratically with the time that you want to simulate, and inversely proportional to the error that you are allowed. Now, this quantum algorithm has been, in the meantime, improved by a lot. So now the most efficient algorithm, the quantum computer, scales linearly with n, linearly with time, and logarithmically with 1 over epsilon, 1 over the error. And so that's very, very efficient, because you should compare this with this exponential time that it requires a classical algorithm. So there's a huge advantage. So indeed, you can build a quantum computer, then you will be able to solve dynamical problems much more efficiently than with classical computers. And in fact, this algorithm here, this totalization, can actually be translated very easily to nice devices. So this is why Google is trying to do this, apply this algorithm to solve certain problems already. This one is not so easy. This one requires many gates, extra gates, let's say. And so that's not good for nice devices, for the first is. And also for analog computers, and for analog computers it's even simpler, because you are able to engineer your qubits in such a way that they interact according to this Hamiltonian. The only thing that you have to do is just to wait, because the interactions will go, the Hamiltonian would drive the evolution, generate the evolution, and this is the evolution that you want to create anyway. So in summary, dynamics is very efficient with quantum computers. What about ground state? Imagine that now we want to compute properties of a ground state. So what is the problem? The problem is that I have my Hamiltonian, and now let me diagonalize it. So let me compute the eigenvalues and eigenvectors of this Hamiltonian. And so there will be this will be the spectrum that I am represented here. And we are interested into the ground state. So the eigenstate corresponding to the lowest energy, that's the ground state. And the problem is that we would like to compute some physical properties, some expectation value, some observable in the ground state of this Hamiltonian. This appears, for example, if you're studying problems at 0 temperature, that's the problem that you want to solve. And so how can you solve this with a quantum computer? Well, it turns out that that's a very hard problem, even for quantum computers. So people have classified the difficulty of problems. That's what is called the complexity analysis. And you probably know that classical problems can be classified depending on how long does it take to solve or to check the problem. So for example, P are the class of problems that can be solved in polynomial time. These are decision problems that can be solved in polynomial time. For example, multiplication can be efficiently solved with a classical computer. And P are the class of problems that cannot be solved efficiently in polynomial time, but can be checked efficiently. For example, factorization is very difficult to find the factors of a number, but if I give you the factors, it's very easy to check. This is why it's in the class in P. BQP are the problems, the equivalent to P, is like the problems that a quantum computer can solve in polynomial time. In QMA are the problems that a quantum computer cannot solve in polynomial time, or may not solve in polynomial time, but can be checked in polynomial time. And it turns out that this problem that I mentioned here is in QMA, meaning that it's expected that even a quantum computer will require an exponential time to solve it. So this means that for solving the zero temperature problems, then the time in a quantum computer would scale exponentially with n. Still, however, I mean, this may be more efficient than a classical computer, because in a classical computer, I mentioned that if you just say that you're only allowing a memory that grows linearly with the size of your system with n, like it's in the case of the quantum computer, then it would take even a longer time like that. So there is some quantum advantage, as you can see here, you take into account also. So let me very briefly tell you about some algorithms to solve ground state, to find the ground state. And let me just give you one that's very naive and very basic. And it's the following. Just take your system and prepare a product state. Okay, so a state in which the state is in a random state. The state is the first qubit is in a random state. The second qubit is in a random state. So all the qubits are in a random state, in a product state. And so this, of course, you take this product state and you write it in the basis corresponding to the eigenvectors of your Hamiltonian. It will be a linear superposition of them. And these coefficients here could be random, basically random, because your product state is random. And so what you could do now is to measure the energy. And so if you measure the energy of your system, you measure this observable H, then according to quantum physics, you will obtain one of the eigenvalues with a probability that is the coefficient that you had in front square. So maybe by chance, you measure the ground state, and therefore, then you will have prepared the ground state. You measure the energy. So the probability for that, of course, it would be this coefficient square. And this coefficient square, you have a random state, typically would be 1 divided by 2 to the n, because there are 2 to the n vectors in your Hilbert space. So the algorithm could be like that you prepare the state, you don't know what is the energy. So you measure the energy, get the value, then you prepare another state, get another energy, then you're noting what is your energy. So here, you're writing what is your energy. And at some point you do many, many measurements, 2 to the n, maybe n times 10 to 2 to the n. So then you're sure that your ground state energy has appeared. So you just choose out of the ones that you have written, what is the lowest one. And once you have the lowest one, then you know what is the ground state energy. So you continue repeating the experiment until you again measure this energy is zero, and then you know that your state will be the ground state. And once you have that, then you measure an observable, and in this way you will have it. And then it's very simple to see that the computational time would be 2 to the n, right? Maybe some factor times n, something like that. And actually this is exponential, as it should be, because of what I told you before. And however, it turns out that this algorithm doesn't work. And this doesn't work. And the reason is because I told you measure the energy. How do you measure the energy? So the energy is an operator that is a sum of operators. And it's relatively simple to measure each of these operators separately, but not the sum of all of them. This requires to make something together in the whole system to measure that. And that's not possible in principle. And so therefore, what you will have to do is to measure one of these observable, one of these Hn. But of course, you measure one of these Hn or few of these Hn, then you will not project into the eigenstate, so this algorithm doesn't work. So as I explain it, the algorithm doesn't work. You have to do something else. And this something else was invented by Kitaev back in '95. It's called phase estimation. And that's a quantum algorithm that basically allows you to measure the energy. And the idea is very simple. What you do is that you have some state psi, and imagine that this is one of your eigenstates of your Hamiltonian. And now you have some auxiliary qubits in state 0, some extra qubits that you have to use. There is some circuit that you can do in such a way, the state after running your circuit, and this is quantum algorithm, for your qubits will be the same as you have, and the qubits here will encode the value of the energy. Okay, so there is an algorithm for which you have to be able to perform the dynamics, but I told you before that the dynamics, you can do it efficiently. And this algorithm, you use certain tricks. Then what we will do is that you have your product state and a linear superposition. Then by linearity, it will create a superposition of these states in which your ancillary qubits will encode the energy. So now you can measure in binary, let's say. So now you can measure this energy, and then you will get the energy, and then you can use the algorithm that I told you before. And so this works. So the question is that, of course, you need some overhead here, because you have to do that. You have to apply this algorithm in order to do that. In fact, there is a way of accelerating this algorithm and to do it even faster. And the idea is to use another well-known algorithm. People call it Grover algorithm. So in general, it's called amplitude amplification. And it's an algorithm that it allows you, so you're able to prepare some states, let's say from a trivial state to prepare some state and going back and forth with some unitary operation, with some circuit, then it allows you to amplify one of the coefficients here. So for example, the alpha 0, and to make it 1. And the number of computational steps that you have to do is actually inversely, inversely like the absolute value of the coefficient. So what you see here is that now this algorithm would be faster because it doesn't scale like 1 divided the probability, or the number of repetition doesn't scale like 1 divided by alpha 0 square, but like 1 divided by alpha 0. So this is faster. Now you can put together everything that I told you. There are many details because, of course, the phase estimation, because the energy, you have to get some digits. And so otherwise you will have to use an infinite number of ancillas, but it would require an infinite time. So you have to make cutoffs, and then you do some mathematics to compute what is the time. And then you see that you use the phase algorithm, then the computational time scales like 2 to the power 2n divided by epsilon. And you use amplitude amplification. So the trick that I told you later on, then you can improve such a way that this increases like 2 to the 3n halves divided by epsilon. So now I'm going to talk briefly about some methods, some algorithm that we published some years ago, which scales better than this algorithm. So it scales as 2 to the n halves times logarithm of 1 over epsilon. So it's better in the error, it's better in the scaling with n. And of course, you may not care that this is a n halves, it's over 3 n halves, but of course, if you have 10 to the 20 or 10 to the 60, then it makes a difference. So this is a cubic of this number here. And depends on delta, and delta is what it's called the gap. And so it's the difference in energy between the ground state and the excited state. So this gap may depend on n. So typically, if you have critical systems, this gap decreases like 1 divided by n or 1 divided by n squared. So this means that there will be some polynomial factor in front for typical systems. And let me tell you what is the idea, because I will use it later on also for finite temperature. The idea is like before, that you take a product, a random state. So you can write it as a linear superposition of the energy eigenbases. And then you just, what you do is you apply this operator to your state. This is called a Gaussian filter. So this is an operator that depends on your Hamiltonian, some E, which we call energy, and some parameter delta. And you see that this is a Gaussian, which is centered around E, and it has a width delta. So what this is going to do is, if you have a superposition of all these states, it will filter out the ones that are around some region of width delta around the energy E. Okay, so the state that resolves is a state that doesn't have basically contributions from up here and down there. It's only from here. And now the idea is that if you take this delta and make it shorter, then you can use phase estimation and amplitude amplification, as I told you before, well, or phase estimation to compute what is the energy. And then by doing this with different filters and using bisection, then you can find what is the ground state energy. And once you know what is the ground state energy, you can prepare the state just using this filter. And so, however, this filter is a non-unitary operator. So how do you apply a non-unitary operator to a state? Well, the idea is to Fourier transform it. So you can write always a Gaussian as a sum of exponentials of e to the minus ht. And then you see that this is the evolution operator. So in fact, you're able to do the dynamics with your system, and to create linear superposition of dynamics, then you will be able to apply this operator. And so indeed, that's the whole idea, that you take the state P, and then you apply some quantum algorithm, and that's because there's a complication that I'm not going to explain here, which will create the state. this state is not normalized. And so what it means is that this will happen only probabilistically. And this is why this this takes an exponential time to this algorithm. However, you use phase estimation and amplitude amplification, you can speed it up, and at the end you get the scaling that I mentioned before. So with this algorithm of filtering, there is a better way of producing ground state. However, this method here and the previous methods cannot be used neither with analog nor NIST devices. And so that's the, and that's why that's only useful for, let's say, full-fledged quantum computers. There exist some other quantum algorithms which are heuristic, meaning that you cannot prove that they will have any acceleration. So they may even work worse than a classical algorithm. And so one of them is the adiabatic algorithm. Another one are variational algorithms. They're very popular at the moment because both of them work with either analog quantum computer or NIST devices. So people are trying to solve many-body problems with these kind of algorithms, especially with these variational algorithms. However, as I mentioned before, they are heuristic and nobody promises that this will work better than a classical computer. In fact, for some of the problems which people have used so far, they are not better than classical computers. Okay, so I'll move on now to finite energies and finite temperatures. And so what I will do is I formulate the problem first very qualitatively, then more precisely, and then I will tell you how a quantum algorithm can solve this problem. So again, the problem is to compute some expectation value with some E. But now this E, this is the state, instead of being the ground state, will be some finite energy state. This is what we call it finite energy. So not the ground state, but some state, let's say we have some other energy. And so for that, I have to draw the spectrum and tell you a little bit of properties of the spectrum. So this is the spectrum of this Hamiltonian. And it's very easy to see that if this Hamiltonian is local, then, well, first of all, if you have qubits, then there are 2 to the n states. Eigenvalues in the spectrum, right? Because the size of your Hilbert space, and you have a local Hamiltonian. It's very easy to show that they accumulate, the states accumulate at the center. Here, there are more states here than on the sides. And in fact, I mean, this is the ground state, and this is what I will call a finite energy state. So when I say that I want to compute finite energies, what I mean is that I want to prepare a state that's somewhere here, and then compute expectation values in that state. But I wanted to formulate a bit more precisely, and for that, and in a more useful way, that's a more physical way. So for that, as it's interesting to introduce, it's important to introduce what is called density of states. So what you can do is now to take some interval and count how many states are in this interval, and then plot this here, then take this interval, move it a little bit to the right, you count how many states, and then you will see that you will have a curve that will look like that. So it could be actually, this would be like with staircase. Like that, but it's more pronounced in the center because there are more states, and that's what I told you before. Now you increase the number of qubits to 15, then first you will have many more states because there will be 2 to the 15 instead of 2 to the 8. And you look at the density of states, so you will see that it will be like that. The width you can show, it's very easy to prove, that scales like square root of n of this curve, of this density of states. Now in physics, and in many other, in other subjects as well, then it's important to notice that the energy is an extensive quantity, meaning that this Hamiltonian is a sum of terms, and there are capital N terms, so as many as qubits. And so the energy typically will scale with M as well. And so you take a state and you measure the energy and you increase the size, and you take another state and measure the energy. So typically this will grow like N, no? Because there are N terms in your Hamiltonian. So it's good to define intensive quantity, just to take the energy and divide it by N. And this is what is called the energy density. And now we can plot the density of states in terms of the density, energy density instead of the energy. And so what you see is that we will have the same curve as before, but now it's narrower because we have divided by N. So as we increase N, it gets narrower and narrower and narrower. So it's not extended because we have divided by N. But now this, instead of being N, the square root of N, now it's 1 divided square root of N because we have divided by N. So now the density of states, as you see, is very narrow. And now the idea of the problem that we want to solve is just to give some value for this intensive energy This would be just to fix this energy and to have an algorithm that gives the physical properties for states that are with this energy and to see how this scales as we increase this capital N. So now I can formulate it more precisely. So we like to fix some energy density, small e, and then take n qubits, and then take E equal to NE to fix this energy and to prepare a state which has this energy. Actually, since this is a discrete spectrum, because we have a finite dimensional system, and it turns out that this energy will not be an eigenstate. So that's why we have to be, to be precise, what we have to give is a little width here. So the formulation of the problem will be that give me some fixed energy density, give me some observable, and what we would like to do is to compute the expectation value of this observable in a state psi, and we require that this state psi is the mean value, this energy that I gave you, that I fixed, which is equal to this n times E, and the variance is equal to delta. So here I give you E, I give you O, I give you N, and I give you delta, and I give you some prescribed error. So the goal is to see how to solve this problem with a quantum computer scales with N and also with epsilon and delta, which are the parameters that I gave you. And so now you want to relate it to physically relevant problems, then it turns out that, so how should I choose delta? Then it turns out that you want to get thermodynamic variables, so you want that your quantum algorithm is able to give you something that we can take the thermodynamic limit and they give you the thermodynamic value, that this limit exists and gives you some value corresponding to what would be, you would take an eigenstate, then you have to take delta as 1 over n. So keep it in mind. So the delta here, in order to make something that is useful for physics, has to scale like 1 over n. Okay, let me now formulate the second problem. It's what is called problems in thermal equilibrium. So now you don't fix the energy, you fix the temperature. So you consider a state which is a Gibbs state. It's a thermal state, temperature T, K is Boltzmann constant, and C is just the trace of e to the minus beta h, so it's a partition function. And so what you're going to do is just to weight each of the states with this probability distribution, with a Boltzmann distribution, and then you want to average the value of some observable with respect to all the states with the corresponding weight, which is this P of E, and for each of the states that you have there. So the problem is, and you fix the temperature. This is the problem here. You fix the temperature. I give you the temperature. I give you the observable. I give you the precision, and then you have to compute this trace with this precision. And we want to know how does the time scale with n and with epsilon and with temperature, for example. Okay, so now let's go to the algorithms. So let's first look at some classical algorithms that solve this problem. Actually, there are many algorithms, so maybe some of you are working with those algorithms already, but just let me a couple of them that are very popular. So one of them is tensor networks. And so, for example, you can use tensor networks in one dimension to solve these kind of problems. And then you can show that with tensor networks, the time that it requires to answer the question that I gave you for finite temperature, the time scales like 1 divided by delta. And the idea, for the ones who are familiar with tensor networks, is that when we are filtering the product state, we are producing a lot of entanglement. And the tensor networks have a hard time to produce this entanglement, to describe this entanglement. And so while delta is getting narrower and narrower, you produce exponentially entanglement, and that's why it's hard with this system. So in fact, you scale delta as 1 over n. So I told you that was relevant for physical problems. Then this time grows exponentially with n. And that's why this problem that was mentioned is hard for classical algorithms. So classical algorithm, exactly solvable, even tensor networks, which are the most appropriate for this kind of problems, that the most appropriate that we know, at least, then scale exponentially with time. Now for finite temperatures, actually there is a very useful, a very good algorithm, which is called quantum Monte Carlo, that is used both in condensed matter physics and high energy physics. And this works very well, scales very well for many problems. However, there are some problems for some Hamiltonians for which this doesn't work. There is, in that case, something that is called the sign problem. And if you have a Hamiltonian that has the sign problem, which are generic, in fact, then this Monte Carlo algorithm will require an exponential time. And so what I'm going to tell you now is about the quantum algorithms, and that have a speed up that either you have an exponential speed up with respect to the classical algorithm, or, as I will mention, that circumvent the sign problem in quantum Monte Carlo. So first of all, I mean, just to start, let me tell that the problem as I formulated included the zero temperature problem, because I could have given you the energy equal to 0, and therefore you will have to solve the zero temperature problem, but we say that this was difficult, so this was exponential. So this problem in general will be exponential, so it will be exponentially difficult with a quantum computer as well. However, what may happen is that starting from some energy is not longer exponential, but is polynomial. Or if you want, starting from some temperature, then it is not exponential by polynomial. And I will show you that this is the case. Okay, so that's the first algorithm. Again, there's the energy, there's the algorithm. I propose two problems. One is finite energy, the other one is finite temperature. Let me talk about finite energy. So people will relate it to microcanonical ensemble and statistical physics, but this doesn't matter. So you fix this energy density, and then you would like to take this state, which has certain width around this, and see how you grow and how the time takes. And then you already see here that why is difficult, the problem. The problem is difficult because most of the states are in the center, and there is only an exponential. This is kind of a Gaussian. There's a Gaussian tail coming here, and you're interested in states that are in the Gaussian tail, and therefore there are few states. However, even though there are few states, there are still some states here which can be easily prepared. So, and that's what I want to use. So the algorithm, what it does is that first creates a state at this energy that you're asking me, and this state will be easy to prepare. However, this state will be completely useless because it has a width that is very big, not the prescribed width that you gave me. It was 1/n. Instead of having a width 1/n, will have a width which will be square root of n, will be huge. So the state will be completely useless. So the next step, what we'll do is that we'll apply a spectral filter very similar to the one that I defined for zero temperature. So we'll make it narrower, this distribution, in such a way that now is delta, and that's what you were asking for. And so I will have the state. And so in principle, I could prepare this state and now perform measurements, but the algorithm doesn't do that because this is very expensive and that's not so efficient. It's much better never to prepare state, but to do some with a quantum computer, some auxiliary computations that will not prepare the state, but will allow you to answer the question that was asked, namely, what is the expectation value of your observable? So let me tell you a little bit in detail, what is it about? So first, we take a state that is easy to prepare at that energy. For example, it could be a product state, like I mentioned before. And so it's very easy to take a product state, and if the energy is sufficiently high, but still, I mean, can be very low, in fact, then you can prepare a product state with this energy. The product state has, though, as I said, some variance, some distribution of energies, which is very broad. And in fact, of course, if I compute any observable with a product state, we will have nothing to do already to do with the Hamiltonian. So in fact, I will not have correlations. Whereas, of course, if I have a Hamiltonian, their interactions, I should be able to measure correlation. So that's why the state is not useful, even though it has the right energy. The fact that it's very broad means that it's not the right state to describe the thermodynamic properties of my system. So this is what I mentioned before. So for some, there's always some energy density for which it's always possible to find a product state. This was proven by Lieb many years ago. And even if you want some energies below this E, then you could use some other algorithm, like an adiabatic algorithm or the variational algorithm that I mentioned before, to lower the energy. And then, I mean, then we don't promise that this will work because this algorithm may not work, but still, I mean, in practice, you could use that. But in any case, I'm going to assume that you're giving an energy for which I can prepare easily some state with that energy. But notice that this is a restriction. And this is what I told you, it cannot work for all energies because then it would solve the zero temperature problem, which cannot be solved. Now, the next thing is to narrow this variance, and the idea is to apply the same filter as before, again, and to write this energy Gaussian filter as a linear superposition, like as I've done before. However, now we don't want to create this state. And you see, this state is a linear superposition of states evolved at different times. So it's a kind of a Schrödinger cat state. It will be very difficult to be produced by, say, an analog quantum computer or one of these near-term quantum computers. So instead of that, you use the following trick. Okay, well, first of all, maybe let me mention that in this expansion, then you can easily show that the number of terms that you require is case like square root of n divided by delta. This is the prescribed variance that you gave me. And the maximum time that you have to run decreases like 1 over delta. And that's good news because you see that the time that we will require and the number of times that we'll have to do things only scales polynomially with n and with 1 over delta, not exponentially with 1 over delta. However, this state is not normalized and it's very highly entangled. That's what I mentioned before. So this is why we want to do it in a different way. And that's the third step. And the idea is to never compute, so if you want to compute it, never prepare the state. However, you see, we have this state and we can replace it in this formula. And so we will be able to write this O now in terms of P's e to the minus IH times O times e to the minus H and P's. So it can be written in terms of these quantities. It's very easy to show that O would be a sum of this quantity divided by another sum of this quantity. So the idea is to use the quantum computer to measure this quantity. And once you have these quantities, then you use a classical computer just to plug in the formula and to compute O. So you never prepare the state, but you have to compute these quantities. And this is what is called typically time series trick. And in practice, I mean, I don't want to enter into that, but these quantities, I mean, can be even measured very efficiently for many Hamiltonians. If the Hamiltonian has certain symmetries like Hubbard models and Hamiltonians, many spin models and so on, they can be very easily measured because they require to measure just the absolute value of this quantity. In other words, the phase can be efficiently computed classically. So you only have to measure the absolute value of these quantities, and the absolute value of this quantity has a very simple interpretation. You start with some state, you evolve, and then you measure the probability that you end up in the same initial state. So for example, you have a quantum simulator, you have some spins, you prepare the spin, you evolve, and then you check what is the probability that you end up with the same, exactly the same state that you started with. You repeat it many times. Sometimes you end up, sometimes you not. You assign a 1 whenever you end up, a 0 when you never end up. Then you compute the average value, and this would be the probability, and this will be this quantity, and the same thing with the B's, and then you replace in the formula, and that's how the algorithm works. And so the quantum algorithm prepares a product state, evolves it for the time that is with the dynamics that I mentioned before, just using the dynamical method that was very efficient, and it evolves for times up to 1 divided by delta, and then measures and repeat it several times to compute these quantities A and B, and then it does the same thing for many of these times. And at the end, you compute the classical expectation value of a classical computer. Now you have to do some mathematical proofs and so on. And at the end, you realize that actually the time that it requires in a quantum computer to compute this quantity is case like n, 1 over delta, and 1 over epsilon, some polynomial. So it's polynomial, and therefore there is an exponential speed up with respect to the classical algorithm. Even if delta, it's case like 1 over n, then this will be polynomial in n. And so it's an efficient algorithm, and with it, you could do some things that you cannot do with classical algorithm. And what is interesting is that, I mean, in the paper, I forgot to quote it. So in the paper that we wrote about this algorithm, in fact, we showed that it can be used with analog quantum computers and also these mixed devices. And to finish, now I will talk about the finite energies, finite temperature. And the idea here is to use the quantum computer, so actually to solve this problem with a classical computer using sampling, okay, using the quantum Monte Carlo, the same thing that you would do with a classical model. However, to use the quantum computer as a subroutine that overcomes the sign problem that I was mentioning before, that appears in quantum Monte Carlo method. Okay, again, so now we fix the temperature. We want to compute this quantity, this expectation value. And so what you would do is to, I mean, this is what is expressed here, is that if you realize that this observable can be written, this is the formula, and then you can re-express, you can write the trace as a sum over product states. And if you express it, just believe me, then you can see that it can be written as something that is positive sum over product states and energies, and then some quantity, and then the same sum that is positive. So you see that you can interpret this as some probability, and so you have to compute some expectation value with some probability. But what is nice is that this probability, actually, and this quantity here, depend on these A's and B's that I told you before with the previous algorithm. So in other words, what you could do is to take a product state classically. So you decide spin up, spin down, spin down, spin up. You just take a random state. And now you compute this probability with a quantum computer. You can compute this, even the product state and some energy, fix the energy. Also, you choose a random energy, and then you compute this probability. Now you change a spin, and then you compute any random spin, and then you compute the new configuration and the new probability. And you do it with a quantum computer, no sign problem, because you can compute this efficiently. And depending on that, then you choose or you admit or not the change. And in this way you sample, and in this way you will compute this quantity. And then we know that the convergence of that will scale like 1 divided by the square root of the number of samples. Okay, so this is like using Monte Carlo, but using the quantum simulator as a subroutine, or the quantum computer as a subroutine for this Monte Carlo. There is no sign problem because this quantity is positive and can be efficiently computed. This is not what happens when you have a sign problem in the classical method. However, I mean, the price that you have to pay is first that there are more measurements, and this is because you have to sample. So you'll have to do many more measurements because you have to choose energies and product states. Still polynomial number of measurements, so still scales polynomially. And the other thing is that when you have a sampling, even classical Monte Carlo, then you can never make sure that the sampling will converge fast. So you may have a bottleneck in the sampling or something like that. And therefore, its part doesn't have sign problem, but still, even like in classical sampling methods that they don't have sign problem, then still, I mean, you have to hope that it works in practice. Okay, and this can be used with analog and NIST devices. So what we did is actually to check this algorithm. So what we took is a problem, a Hamiltonian, that we can solve in a different way. We can solve, this is a Hamiltonian that there is an efficient way of solving with classical computers. So you can map it into free fermions, and then you can solve free fermions, and then simulate the quantum computer now acting with this Hamiltonian for 20 qubits or for 100 qubits and plot it. And that what we saw, I mean, I don't want to here bore you with the results. So we computed this, how the quantum computer would compute the magnetization and compare with exact results. And that's what you can see here for 100 qubits for values G equal 1 and H equal 2. This is like the coupling constant, and this is like a magnetic field that you have inside. We did it for different values of delta, for delta equal 1 and delta equal 4. And what we saw is that it scales very well. So it coincides with the exact value. And so, I mean, the quantum computer would work very well. And we also added 1% error. So assuming that every time that you measure, there is a 1% error, and we can simulate this error. And so what will happen with the quantum computer? And we see that still the errors would be relatively small, right, as compared to the numbers that we have here. So this is actually, it's not m delta, it's m delta actually minus this straight line minus the exact result. So anyway, you see that this will work. This for the experts, and this has a 0 temperature quantum phase transition for G equal H. And so what we can go is for the critical region, and then there it also works well. So it doesn't realize that there is a critical region or not critical region for this particular problem. So, okay, so that's we did also for the finite temperature, and yeah, right. So at the end, I have presented, so that's a summary, quantum algorithms for 0 temperature, finite energy, finite temperature, also dynamics. For the 0 temperature, this takes an exponential time. For finite energy, proven polynomial time. For finite temperature is heuristic, but there is no sign problem. And these two can be used with NIST devices. This one cannot be used with NIST devices. So the requirement is that you should be able to prepare states with the desired energy, and for example, product states, and you have to be able to evolve to apply the dynamical algorithm and to measure with that algorithm. And so what we're looking at the moment is, so we are collaborating with some Google in order to use the quantum computer in order to build this, and also with some people building analog quantum simulators. And so we are we are looking at ways of mitigating the errors that they have in the experiment in such a way that this would work better. So we are adapting it to different platforms. So one of them, the most important, cold atoms and optical lattices, or superconducting qubits. We are also developing some other quantum algorithms based on this idea that we mentioned, that would solve not finite temperature, but some optimization problems. And we're also using, together with tensor networks, to inspire some classical algorithms. And so with that, I would like to finish and thank you for your attention.
Okay, thank you, Ignacio, for the very good talk. So now I pass to the YouTube questions. First, we have Egan Viana. When do you think the industries will be able to build efficient quantum computers to be used in research laboratories?
Industries are building quantum computers. IBM is selling quantum computers. And so they can sell, I mean, you can buy a quantum computer if you have a few millions of dollars. And however, these quantum computers have a limited number of qubits, have 20, 30 qubits and have errors. So the question is, so how will this evolve with time? So people expect, actually IBM expects that they will be able to have 1,000 qubits in 3 years with relatively small errors. However, I mean, one has to say that 1,000 qubits with errors, it depends on how much is the error to see whether this is useful or not. And so this will depend on how the errors are. And this will still be NISQ devices. These will not be scalable quantum computers. So they will have limited uses. So for example, it will be useful for the algorithms that I mentioned here, for some other quantum simulations. And there are many people investigating. So there are problems that could be solved with these, let's say, faulty devices. However, that's not very clear what are the problems that can be solved. Now, if we wait for a longer time, then we hope to have fault-tolerant, error-corrected computers. So these are computers that don't have errors or that correct the errors. And this will be very useful because then you would be able to solve optimization problems with them and to solve, I mean, many other problems. However, this will require a long time because they have to scale the current devices, and that's a very big technological problem. Optimists talk about 10 years, and some of the people say that quite longer than that. And so I don't know, I would say that I would expect that probably not in the next 10 years.
Thanks. Another question also by Egan Vianas. Are you already able to apply the algorithms in the laboratory, or they are only theoretical?
We are collaborating with people in laboratories to use them. And in fact, so what we are doing is adapting them to the different platforms. And so we have collaborations with experimentalists for doing that. So at the end, we have not proven yet, because what we want to make is a clear case that in the presence of the errors that they have with current devices, they will still work, and they will still demonstrate that they work. And so for that, we are doing some theoretical studies. But once we have finished them, we have talked to experimentalists that would like to run them with their setups.
Thanks. A related question. Those methods to calculate the ground state energies and average of some observable can be applied in critical or topological phases? Definitely.
Yes. Definitely. Yes. In that case, the question, if somebody studying topological phases knows that the observables, you compute the expectation value of observables, they don't have much information. So typically you have to take string operators. And so the observables O will have to be string operators because you would like to do something that has a non-trivial expectation value. But yes, so there is no restriction to that.
Another question by Nathan Berkowitz here. So do you have a prediction when an analog quantum computer will be faster than a classical computation for lattice QCD? And how much will it cost compared to the classical computer? Okay.
So I hoped that you didn't ask about lattice QCD. I hope that you ask for condensed matter physics problems, because this will happen very soon. And there are people who claim that this has happened already. And so I would expect this to happen very soon, that these analog computers would solve quantum many-body problems that are interesting in condensed matter physics, in particular Hubbard models and spin models, relatively soon. For lattice QCD, this requires a lot of effort. So first of all, they will probably relatively soon work in 1+1 dimensions. And then that's probably not what people in high energy physics are interested in. You're interested in 3+1 dimensions. And there is a very long way to go there. And the reason is because if you have a lattice formulation of gauge theories, or lattice gauge theory, Then in higher dimensions, then you have plaquette operators. So your magnetic field is represented, even for abelian and non-abelians, as a plaquette. So it requires four-body interactions in terms of the diagram that I showed. And these analog quantum simulators are very good in engineering two-body interactions, but not four-body interactions, because in nature, these atoms interact with two-body interactions. You have to engineer four-body interactions, and you have to do it with perturbation theory. And in perturbation theory, you go to fourth order, you will get effective Hamiltonians. But of course, this means that your effective theory, let's say, is fourth order perturbation theory. So all the couplings are very small. So this requires very, very low temperatures. And they are much lower than the ones that are currently used in experiments. And so this tells that this is very difficult. So I would say that if you go to 1 + 1 dimension, there's still some problems that the lattice gauge theories that we cannot solve with classical computers. And the reason is these are quench problems. So problems of dynamics, where you shake your system and then you study the dynamics of that system. So Monte Carlo doesn't work for that. And many methods, Gaussian methods, don't work for that. And this is where quantum computers probably, these quantum analog simulators, may be able to solve some problems in lattice gauge theories in a relatively early time, years, let's say, from now. However, of course, these have limited interest. Okay, the big problems are to solve, let's say, SU3 kind or Yang-Mills theory in 3 + 1 dimensions and with chemical potential. Okay, so problems that are really relevant and difficult.
Thanks. We have another question by Angela Foster. Which are the advantages of each platform?
Okay, yeah. So I would say it's a very nice question. So, and let me mention some platforms. So one of them is superconducting qubits. Superconducting qubits, this is what Google has, what IBM has. These are very good for these NIST devices and for scaling up to 1,000 qubits or something like that. And the reason is because you can use some nanofabrication methods to build many of them, many qubits. And so that's easy to scale. However, I mean, it's difficult because this nanofabrication has errors. So it means your qubits will not be perfect. And also you have to be at very low temperatures in dilution refrigerators, and it may be technologically difficult just to connect many, many qubits, put cables in the dilution refrigerators, and is to set them at millikelvin temperatures. And so that's why they're good for that. And there are trap ions and cold atoms, and especially trap ions and cold atoms, I think that they're very good for analog quantum simulators. And so because it's very easy to engineer Hamiltonians with them, there are many tricks and they work very well. And so I would say that those are very good for analog quantum simulators. And I would say that also for quantum computing, for NIST devices, that's what people claim with trap ions. With cold atoms, not at the moment, they are not competing. However, I mean, maybe some of you have heard that there is a fantastic set of experiments in Harvard and Caltech and some other places, in Paris as well, in which they have been able already, they have already 200 qubits. So this is more than what they exist in superconducting qubits. And they promise that they will have errors that will be of the same order of magnitude that the ones that they have in qubits. So these are very promising platform. And you should pay attention to that in the next year or so, because probably they can, I mean, they will appear in the newspapers, I'm sure about that. And then there are some other ones like photons. You probably heard that there was also a supremacy experiment in China with photons. So photons are, I mean, maybe suited for something which is called boson sampling. This is an academic problem for which the people don't know what is an application, but it may turn out that they are relevant. So at the moment, I don't see that they are so relevant like the other platforms. And then there are other platforms like semiconductors, so quantum dots or implanted ions implanted in semiconductors. And they, at the moment, they are not so competitive with respect to solid-state quantum qubits. However, they may catch up soon. So they, I mean, there was reported a few months ago that, I think it was months ago, that their qubits, they have much longer lifetimes. And so this opens up the possibility of, I mean, scaling in the same way that they are doing with superconducting qubits.
Okay, thanks. So now I think we can go to the students discussion, right?
Okay.